Have you ever wondered what happens during a contract creation? AKA, when you create a new contract on chain, what exactly happens? The constructor does something, and then some runtime code is being put on chain, maybe, but how exactly does that happen? Why does certain hacks happen where we check whether something is a contract when it calls us, but somehow some contracts can circumvent that because they utilize the hack during the construction phase? How does that happen? There are a few well-known hacks that can occur that way. So I want to make you a better developer by understanding exactly what happens during the construction of a smart contract. This was inspired by some problems that we've been teaching our students at the Rareskills Bootcamp as well. So check that out, rareskills.io. So we're going to dive in today, and my goal is that when you watch this, you will come out of this video really knowing and having a strong visual of what happens during a contract creation. What does the constructor exactly do? Why can we circumvent certain contract checks? And how can we even hack other contracts by utilizing this? So we can become better developers, safer developers, and we can all raise the security of the DeFi field overall. All right, let's dive in. Okay, so I'm going to make the statement that a contract does not exist on chain before the constructor is done. So before the constructor has completed, the contract doesn't exist. But when I say exist, what exactly do I mean? We're going to dive into that. We're going to figure out what that means. We're also going to see why it is. So we're actually going to understand why it doesn't exist in full, let me say. And I want you to have some takeaways after watching this. So takeaway one is, I want you to understand in depth the anatomy of a contract creation on chain. You know, we might not go into 100% detail because it can get very, very detailed. And I guess at the end of the day, you know, we have to actually just look in the Go Ethereum client code. As I'm going to take a step maybe above that, but it's got to be very detailed. I think you're going to have a pretty complete picture. Takeaway two is we want to be careful, again, when checking if message sender, so whoever called us, is a contract. So some hacks have been done where they relied on message sender not being a contract, for example. They wanted to enforce that. We can also hack other contracts that assume that. So that makes us a more defensive programmer. So you'll understand why those hacks are happening. And perhaps you've seen them. In fact, I'll give you some examples if you haven't. All right, so that's kind of the purpose of this. And we're going to see exactly how everything works in this during this construction of a new contract. All right, so it's going to be very visual today, but we are going to dive into some code as well. So I do have remix ready as well in the background. But anyway, let's take a look at some of these hacks and vulnerabilities that rely on the contract or there being code and a contract existing, so to speak. All right, so what do I mean? We're going to look at example one here. It's an example from Solidity by Example. Excellent website. Definitely check that out. What they've done here is they have created a target contract. All right, it starts here, it ends right here. This target, just imagine it's some target contract. Doesn't really mean what the body is here. The point is they have a function here that checks whether something is a contract. You can imagine it being a modifier or a function, but it checks whether this account, okay, which is an address, whether that is a contract, and it returns a Boolean saying true or false whether it's a contract. All right, so what do they do? They use a method which relies on the code size of this external account. All right, so they're gonna use YUL like through this assembly block, and they're basically going to call this address to this account. They're going to get the code size, so basically the size of the code of that contract, and they return that here in size, and they're going to say, is there any code at that address? Well, then the size has to be bigger than 0. If it is, yes. So then true, it's a contract if there is a code there. So EOAs, meaning, you know, there are two types of accounts in Ethereum, right? One is a contract account, and the other one is an EOA, an externally owned account. So there's a human account. It is just my wallet, your wallet, and so on. That doesn't have any code sitting there. There have been some recent developments that make certain changes to this in general, but you know, it doesn't have any code. The contract definitely does have code if it's deployed. Okay, so the point is that at some point during this target contract, they're saying, hey, I want to make sure this is a protected function. It's protected in the sense that I want to make sure that no contract is allowed to call this function. All right, so I'm going to make sure that it's not a contract, whoever message sender is. Okay, and they rely on that. So you can hack this because this assumption that the code size is 0 fails during construction. So what I mean is, this Solidity by example, they show you the hack. All right, you can hack this by, during construction, you see this, the constructor, you can point to this target address up here, and you can say is contract, you can call target that is contract with address of this. So we're asking the target, hey, I just created this hack contract. Do you consider me a contract? Yes or no? The answer is no. This will be false, is contract. And the reason is because we're calling during the constructor, this is contract. And during the constructor down here, the hack contract has not been deployed on chain yet fully. All right, we'll show exactly why. So it hasn't been deployed, so there is actually no size of this code, so this will be false. And then, in other words, we can call this protected function, even though they didn't want us to. All right, so that's because they're relying on there being code on this hack contract, but there isn't during construction. All right, so we'll see why. The other example is from Rareskills.io. It's a contract that's called Dumb Bank, and basically what this is there's just some balances that are mapping addresses to values. So just a standard bank here. You can then withdraw. It's called dumb because it's reentrant. It's exploitable through reentrancy. But then a bank robber comes along and, he wants to rob the bank. And basically, during construction, he's trying to be smart here because during construction, he's trying to rob this dumb bank. He calls a deposit. So he deposits an Ether into the bank. He's allowed to do that. And then he calls withdraw. That's fine as well. You can withdraw one ETH. So when you withdraw one ETH, that's fine. This structure up here is reentrancy vulnerable. So what happens is that this dumb bank calls message sender, which is the bank robber, sends money to the bank robber. The bank robber then tries to receive that in the fallback, okay? And then do a reentrancy attack by calling another withdrawal. Okay, what is wrong here? The point is here that during construction, I just said that the bank robber now is a contract, right? Right here, it's a contract. It doesn't exist during construction, really, on chain, right? So when I call this dumb bank will call back down here in the fallback. This happens because it's sending me money, so the fallback will be triggered. But there is no fallback because I don't exist, all right? So the bank robber is trying to be a little too clever here in that they rely on the fallback being called, but since I don't exist, it won't be called. Okay, so we'll see why. It's actually the same problem as over here as in example 1. It's just that like the fallback is just another function, right? I mean, it's the catch-all function if no other function is found, and particularly will be called when you send Ether. So the point is, in these two examples, the problem is because during a construction of a contract, the contract doesn't exist on chain yet. All right, so why is that? So let's take a look. Cool. We're going to study now the anatomy of a contract creation and answer the question, what happens during a contract construction or creation. All right, so we're gonna really start. We're gonna really zoom out here and learn just some basic concepts. We're gonna first start with the blockchain state. The blockchain state is common to everyone. So if I run a node, and I'm part of the Ethereum network, I have a state of how the blockchain looks right now. This and any other node that participates in the network also has a state. These states are all the same. We all agree on this state. Okay, we can make changes to the state, but they're all the same. Okay, now what I'm going to do is try to visualize what this state looks like, and this is inspired by Jordan, Jordan's channel on YouTube. Definitely check that out. I'm going to link to it as well. But anyway, the point is, we have some EOAs. EOAs are like externally owned accounts, human accounts, like Alice and Bob have an EOA. I'm going to color them a little bit yellow here, like light yellow, and I'm also going to say it's an EOA. So this is blockchain. This is the blockchain state at time t. It's a world state in the sense that everybody sees this state. That's what we mean by this world state. That's why Ethereum is like a world computer. Everybody has this state. We all agree on it. But there are also going to be smart contracts in this state. All right. So I'm going to draw them a little bit bigger because typically, obviously, they have more code and more size to them. So that's why I'm just going to show them bigger. I'm also going to show them in a slightly different color. But this is a smart contract. This could be Uniswap v3, for example. I'm going to plot a little robot there, indicating that this is not a human owned account. These are the two different kinds of accounts you can have in Ethereum. And again, this state is common to everything. So it lives on all the nodes in the Ethereum network, this state, and a node is just any instance of an Ethereum client that is connected to other computers also running the Ethereum software. You don't have to run Geth, meaning you don't have to run Ethereum in the Go implementation. Ethereum doesn't require any particular language, but most folks run Go Ethereum or Geth. But anyway, imagine you download Geth on your computer, you connect to some nodes. How do you connect to nodes? There are some seed nodes in the code, but technically you just have to find some nodes. And then once you connect to them, then you're technically connected to the whole network. So when you send transactions to that node, they will start distributing it to other nodes, and in a few seconds, it'll be across the globe to all the nodes, technically, if they're all connected, of course, right? But anyway, the point is, let's say we have some guy, Tom, he has a Raspberry Pi even. He can run Go Ethereum on that Raspberry Pi or some other client implementation. He's just one star or whatever node in this network here. All right, so we imagine this network of all these interconnected systems. His Raspberry Pi is just one of them. He still has this blockchain state, at least if he has a full node, if you will, that has downloaded everything. And then another one could be a validator. These are the validators that are creating blocks. They're running, let's say, a server, which runs Go Ethereum and is also connected to the nodes. I'm just trying to say that Ethereum doesn't assume any particular kind of computer. There's a Raspberry Pi, there's a server. You can have my laptop here, it can be your laptop, whatever. If we just run it, we become another node in this network, and we will join the Ethereum network. But we all share the same state. All right, no difference here. So the state is present in each machine. This is true for all nodes. Hence, this is kind of the world state. We all agree to that. It's not like Tom sees a different state than the validator. All right, so how do we then make a state transition? How do we actually change the state? There are two ways to do that. One is kind of, we can send Ether. This is as kind of a special case because it's implemented a little bit differently than other kind of transactions. So if you just send Ether, that's fine. We're going to go through the example here to just introduce some other actors in the whole ecosystem. And then after that, we're going to look at then what happens when you do a contract creation. Okay, so Alice wants to send Bob 1 Ether. That is what she wants to do. Let's assume she has that 1 Ether. All right. Again, we have the blockchain state. We introduced Vitalik. There's no reason to do this. He's not going to be important in the example, but he did create, he was one of the core creators of Ethereum. So yeah, we'll just put him in there. So this is, again, the blockchain world state at time t. Cool. We have Alice and Bob. And by the way, it's just also to show that any externally owned account, any smart contract ever is present in this world state. So that means on Tom's Raspberry Pi, and again, assuming it has enough storage on that Raspberry Pi, but it actually can see all accounts, Vitalik's account, my account, your account. It's stored on Tom's Raspberry Pi. He can't access it. He can't access your funds because he doesn't have your private keys, but he can see it. Okay, so this is a little crazy that everybody's just sharing. It's a big ledger, right? It's a big, just huge ledger. Imagine like a Google Sheet with Vitalik's account, my account, your account, all the way through like everybody's accounts, including smart contracts, Uniswap smart contract, everything that we just kind of like copy pasted onto all these machines. All right, except it's not a Google Sheet. It's much better, but you know, you can even think about it like that. So that's kind of crazy, but that is true. All right. Anyway, so we have this state. Now, Alice wants to send Bob some ETH. So how can she do this? Well, Alice, the typical way we do this is we connect to our MetaMask. Okay. MetaMask is connected to these nodes in the network. So remember these nodes I talked about before. If you run Ethereum yourself in your computer, you can totally do that. And you can create your own transaction and you can send it out that says you want to move 1 ETH to Bob. Alice could do that. She just needs to be connected to some nodes, and she can also do that. She can manually send that to some nodes, and as long as they send it to other nodes in the network, she'll be fine. But there's some shortcuts, so to speak. There's some software that helps us with that. So MetaMask is one. So when you connect to MetaMask and you say, I want to send 1 Ether to Bob, MetaMask handles all this on the back end. It sends this out to the nodes that it's connected to, and then makes sure that your transaction goes out. But you're trusting MetaMask to do this. So it's a centralized entity. Coinbase does the same. You go to Coinbase, you send 1 ETH to Bob. It's the same thing. They also connect it to nodes. They make sure your transaction goes out. But again, you're trusting a centralized entity. That's fine. And then again, as I mentioned up front, your own local script, you can do this yourself. And then you're not trusting anyone per se. Then you just need to have a list of nodes you can at least send these out to kind of seed it. And then they will send it on to other nodes in the network. And soon the whole network will know about it. All right. Anyway, So Alice constructs this transaction from Alice to Bob, send 1 Ether. There's a lot more included in this in a general transaction. I'm only showing the very basics here. But she has to, if she runs her own local script, you have to do all this yourself. But that's fine. You can get things like ethers.js or web3.js, or you can even do it in Python. There's like a web3.py that'll help package all this up for you. So there's some helper functions. But anyway, now she needs to send this to the node, as I said. MetaMask, Coinbase, they do this for you. You don't need to think about it. Then what the first node does that receives this transaction is it checks that it's valid. Does Alice actually have enough money to send it? Does she have enough gas to send it? Things like that. If it's not valid, it fails. If it is valid, then it gets distributed to the rest of the network. That's also why a transaction costs a certain amount of gas up front, 21,000 gas. This is because all these checks needs to be done. So, and you'll lose that if it fails, if you don't have the money. Anyway, now it gets distributed to this network. So imagine Alice's transaction reaches a node. This node sends it to the other node. Now all the nodes has this transaction. Where does it go? It goes in this thing called a mempool. It's kind of like a temporary place where transactions that people want to put in the block, aka on chain, go. All right. So imagine Alice's transactions right here. Another person, maybe this is Vitalik to me. I don't know. Maybe he wants to send me 1 Ether too. That's this transaction. This is me to you watching this right now. That's me wanting to send you 1 Ether. Then we have some bigger transactions here that I'm just trying to visualize as like bigger chunks in this mempool. This could be a contract creation transaction. And this down here is also a big transaction. This could be calling some big function, some complicated functions in another contract. So for example, this could be me calling a swap function in Uniswap, for example. It's a little bit bigger. It's not just a transfer of 1 ETH, which is rather simple. It's me having to call an entire contract and that function, and then that function does things. So, and I need to maybe use some arguments to call that function. So it typically takes up more space as well. Like it's going to be a longer call because there's going to be some call data associated with it. When I just send 1 Ether, there's no data involved with that. So I'm just trying to visualize these as bigger chunks. But the mempool is like this temporary state of things. It's like a bus stop. It's like a bus stop where the bus comes along, that's the block, and everybody who goes on the bus becomes part of that block, and the bus leaves, and the next bus comes, and everybody goes on. But this is the bus stop right here. It's a little bit messy. There's a lot of stuff here. Maybe there are transactions that again, there's transactions that sends money. There's transactions that calls contracts. There's contract creation and so on. But this is a global bus stop. Everybody shows up here. Now, not global in the sense that everybody has the same mempool, because there can be some delay. So what I mean is, if I run my own on my own laptop, my own geth, and I listen to the network, I will get new transaction coming in sent from other nodes to me, and I will have my own local mempool. But in an ideal setting, let's say that all this information was instantaneously traveled to all the nodes and everybody saw the same, then there would be kind of a global mempool. We would all see the same mempool. The mempool would be local to a computer, but it would be the same, just like the blockchain state. But again, it doesn't exactly work like that. We each have our own local mempool. But just for ease of explanation, let's just say that, that we have this common mempool. Anyway, again, these are small transactions. These are more complex transactions. That's the visual. Now, validators, these are special nodes. You can become a validator too. So this is back in the day what was called miners. You can become a miner yourself or a validator. You can take any role you want to participate in Ethereum, and I encourage that actually. But let's say you're a validator, or at least we have a validator here. They listen to the mempool. They look at the mempool, again, their own local mempool, but they listen to it. And again, this is this bus stop, and the validator then picks who should go on the bus. Okay, it's much more advanced than that. I'm not going to go into those details. So think about it like maybe in the good old mining days, if you will, whereas like the miner just picked transactions from this mempool, or in other words, picked passengers from the bus stop and put them on the bus, and then it mined that, right? So in other words, it created a valid bus, so to speak, and then it sent that bus off. All right. Anyway. All right. So now the validator picks the transaction. Let's just say we got picked. How did we get picked? Well, we paid some gas. Maybe we tipped the validator as well. Please pick our transaction. So we had to pay the gas to do that. We made it up here. This is a candidate block. This is like the bus before it leaves. The validator puts everybody in their seats in the bus right here to be ready for the journey. It might not take off still because it might not be a valid bus, but at least we're going to be seated. We're seated at the top of the bus in the front. and everybody else behind us. And that is because we paid a lot of gas, maybe, let's say. All right, so the more gas you pay, the more likely it is you go on the top here. That's also how sandwich attacks on front running can happen based on this kind of ordering system. And typically, the validator uses some sort of empirical system to order everything. The empirical being just the highest fees paid goes first. But this is not necessarily always the best strategy. Anyway, we're going to execute the pick transactions top down. So we're going to go in order here, and we're going to go to each person on the bus, and we're going to execute the transaction. So we're going to basically say, all right, what do you want to do? I want to send one ether to Bob. Great, I'll do that. What do you want to do? I want to create a new contract on chain. And again, I'm showing this dash thing just because it's not really a focus right now. But the point is, this is doing something. I want to create a new contract. Fantastic. We'll do that. Then this one is like Vitalik sends one ETH to me. Oh, wonderful. I appreciate that. And so on. So it's like we're going order. And the order is important. It's not like we execute this and then we jump down here and execute that and we go back up. The order is important. Anyway, they're executed top down. So let's just say the validator, this will become important later, but imagine to execute this transaction, imagine it kind of sets it aside for a second here over in this execution environment. Okay. Now, because this is just sending one ether, it's not so, the environment is not really the EVM, okay, because it's kind of a special case, but we'll get to there in a second. But let's just imagine for now that we have this kind of, just this red dash box means we're executing this transaction. All right. So we're executing this now. Again, this is just send one ether from Alice to Bob. So now we're going to make a change to the world state. So the validator has, by the way, has copied the world state. They have their own local version anyway. So they just copied it for now. And then they're going to, and the reason I'm saying copy is because they're not actively live updating the world state. Of course not, because the block hasn't been accepted yet. It's just a candidate block. All right. So there's no change. But they still imagine they've taken a copy of this world state and now they're just executing all these transactions here in this candidate block and are making local changes, just local to themselves, local changes to the world state. And they see if all of them are valid, and if everything is valid, then they will propose the block if it's their turn, and then they will actually carry out this world state change. All right. So anyway, all right. So to send one ether, Alice's account will now send one ether to Bob. Behind the scenes, it's just changing the balances easily. Like nothing is actually sent per se, but it's just a balance thing. But now blockchain, this is now the blockchain state at time t+1. So that's how this looks. Now they go to the next transaction, and then they execute that transaction and they make another change. But they assume that this first transaction is important, that this first transaction has happened, right? So they account for that. Anyway, that's how it happens. That's very easy. You send one ETH. Cool. Let's go down to a more complex case. Now, what does Alice want? She wants to create a new contract called Alice's contract. Great. Alice is here. Let's say Uniswap B3 is here. We have Aave here. There's just another contract. This is the world state. You have all contracts ever created. Great. What does she do now? Alice sends a contract or sends a transaction saying that she wants to create this contract. She needs to send the data of this contract creation. We'll get into that in a second. So meaning the data that actually holds the contract logic and all this kind of stuff is not shown here, but she needs to do that. But importantly, she needs to send this to address 0. So that's a special case here. When you send something to address 0, the validator will interpret that as, oh, that's a contract creation. All right. Anyway, still ends up in a mempool, but this time it's this more complicated transaction because contract creation. Validator still monitors the mempool. Validator picks the transaction that creates a contract. It puts it right here in the candidate block. Again, we're at the top, so we paid a lot of gas perhaps. And now we're going to execute this again like we did before. So we're going to set up this execution environment. This time is important. We're in the EVM. We have the stack. We have the memory. We have everything available to us to run through the logic of this contract creation. We'll cover that in a second in detail. But the point is, now we're running this in the EVM. And the validator is running that in EVM on their local machine. We're going to make changes to the world state again, just like before. This time it's not a simple send ether, but it's creating a new contract. But still, we're going to kind of show it from Alice's account in a sense. She sent this transaction to create this contract. And look at that. It's going to be the bigger contract here. And that's Alice's contract. That's fine. That's world state t+1. And it has it deployed now. Okay, so that's how the deployment works. Now, this doesn't really tell us much about what happens during the construction in detail. So let's dive in. All right, so I hope you're all with me so far. That's how a contract gets created on chain. But let's get much more specific. So what we're going to do now is we're going to zoom in. We're going to zoom in on what exactly happened here, because I skipped some steps, right? I just said, hey, the contract creation transaction lands in the execution environment of the validator. Great. They do that and they create the contract. Great. And it ends up on chain. Fine. But this doesn't explain why there's no code during construction. I'm not showing that here. So we're going to dive in right here in this step. What exactly is executed here and what happens? And also, how does that relate to what exists over here in the world state? Why is there no contract code at this address when we're running this during construction and so on? Let's dive in. So we're going to take this red dashed rectangle that we had up here, and we're really going to expand that and see what does this mean when we execute it. Great. Let's do that right here. So we're in that red rectangle. The contract has not been created yet. We're about to create it. We're executing this. So this little box that I abstractly showed before actually means this. Okay, what is that? Let's zoom in. During the creation of a new contract, the following things happen. You need to, as the contract creator, create this constructor code or init code, if you will. That's this part. Wait, I've never created init code, you might say. Well, that's because the compiler, the Solidity compiler, does this automatically for you. Okay, but it technically needs to be done. You need to have some sort of constructor code. Then you also need some runtime code. That's the actual code that goes on chain. And then in some recent versions here and some recent updates, you also have an IPFS hash, as it's called, which is kind of just a verification of how the contract was compiled, all the compile settings, and also like a verification of the runtime code itself. This is used to verify contracts. It's used by Etherscan and stuff to verify contracts that are deployed on chain. So this is just kind of like some metadata, basically, but it does exist and it's important to know. Now, during the construction, okay, this is what's run during the constructor. There are two important things. One is the constructor body, which is the actual code inside the constructor. So if you've ever created a contract, you had the constructor, it does something. If you add a constructor, at least it did something in the body. That's what this is. And then at the end of it, which is what the compiler does for you, it copies the runtime code. So this code, it copies into memory and it returns that to the caller, aka the contract creator. So this, you don't have to manually put. You've never coded that up yourself, I assume. I mean, again, unless you do some sort of assembly stuff. But this is something the compiler does for you. But it's important to know that there are two steps here. So, okay, now when the runtime code is copied back to the caller, that's when the caller can put that runtime code on chain. So it's important to understand that during the constructor body, well, there is no runtime code. So there is no code yet. This gets copied at the end of the constructor and returned to the caller, who then puts it on chain. That's why during the constructor body, there is no contract, because we don't know the runtime code yet. Or at least it hasn't been put on chain yet, I should say. We do know about it, but anyway, so let's see how that works. All right, so this constructor body is run in virtual environment. So the validator, as they're running the constructor body, they creates a new EVM with stack and memory and all this kind of stuff to run the code. Great. So a new stack is created. The constructor bytecode is run. So that's the body of that constructor. And also, at the end of it, this part of it too, which is the copying the runtime code part. So, all right, so we're going to show that as kind of just this stack here, and we're just going to run through that bytecode and so on. And the reason why I'm going up and down there is because the stack is kind of like, it's building top down and it goes up and down. And that depends on how, like, what variables are being put on the stack and taken off the stack and so on. Anyway, and then as I said, as the final part of the constructor, the runtime bytecode is copied to memory and returned to the caller, which is the validator, and they can then put it on chain. So it's important to realize that during this piece up here, which again is the constructor body, there is no deployed bytecode for us yet. All right. And how does this piece work, by the way? Well, we're going to copy the runtime code into memory. In fact, it gets copied to. They just copied to the start of the memory. But the point is, it gets copied into memory. I have other video of what memory looks like and so on, but just imagine as like an array of bytes here. They're going to copy it from some location 0 to the size of the runtime code. Technically, the IPFS hash and the metadata gets copied too, but that's not so important right now. The point is that the runtime code now sits in memory, okay? And then it gets returned to the caller, and then the caller, again, this is the validator, will put that on chain. That's what happens right here, all right? All right, so let's just cover this one more time, because now I want to answer like what exactly happens and what does exist. I told you that during this constructor body, the runtime code does not exist on chain. It's not being put on chain. That's true. But a few things do happen as we start to run this constructor body. Right before we start running it, at least two things happen that we have access to. One is an address is temporarily created, and I mean temporary in the sense that the code doesn't exist yet, but the address does. So the contract gets an address, and you can look at the create opcode or the create to opcode for exactly how the address is calculated. But this will be the eventual address of the contract. This is set up now. Why is this set up now? Before we've even constructed the code and so on. Why can't we just do this at the end? Just go through the constructor, then create the address, and then put code there. Well, because in the constructor, maybe we want to send some ether to the contract as part of the construction. So we need to know who should receive that ether. That's this temporary address. So imagine it's like we want to build a house. The house is the contract code. The house will eventually go on a lot. Okay, it's not there yet. But what we do is we just need to assign some lot. So we go out and we buy a lot. All right, that's what happens before the constructor body runs. So now we at least own this lot. Then the reason is now we can actually send mail to that, right? Send money to it because the lot exists. There's a post, there's a mailing address. The address does exist. There's just no house yet on the lot, but we can send money to it. So that's what we need. Another thing is we also need storage. We can actually, during the constructor, access storage and put things in storage. So in other words, it's like we have the lot so we can go put things on it. It's like we're buying the furniture. We have the furniture before we have the actual house. We can go to the lot and put the furniture on the grass, and it just sits there until the house gets there, and then we can put it in the house, so to speak. Okay, so the point is we just need a temporary lot to do things with until the house is built. All right, so that's why I'm showing it as a smaller box, but still color it as the same as that because it'll eventually be an actual house. These are houses. These are the smart contracts fully deployed. Aave is here, Uniswap is here, for example. But right now we only have the lot. Cool. So we can do things like send ether to that. We can do things like access storage, things like that. But it's kind of a temporary state because the house hasn't been built yet. The house is only built. The house is this stuff, the green stuff. The house is what's being put in memory, returned to the caller, and then the caller says, great, that's the validator. Great, I'm going to go build that house. But we don't have the house yet up here. We don't have the house, but we do have this. Okay. Now, getting there. So, in other words, when the validator, the caller receives this house or this runtime code rather, right? This runtime code, they're going to put it on chain. So they're going to put it right here, and that's going to become Alice's contract. Before, again, it was just a lot. Now it's the full house. Now the contract is done. It's actually deployed. All right. Now the code is there. This placeholder address, or the lot, if you will, hasn't changed. All right. There's still the same address, of course, but we have this contract sitting there now. The house is there now. All right. And now it looks like this. So it's important to distinguish this step from this step. Up here, there is no code. There is no house sitting there. Down here, there is a house. And this step was valid during this constructor body, which is this. Okay, good. Let's see an example. We're going to actually dive in and take a much more detailed look at this. We're going to consider a very simple contract. It's just called a placeholder address. I mean, it doesn't matter what it's called, but it's just a very simple contract that only has a constructor. The constructor is payable. I did that because just to show you that indeed you could send money to that address even before the contract is constructed. This is a very simple contract. It doesn't do anything, just has a constructor. It just takes your money and you can't get it back. So please don't run this in production too. Anyway, how does this look at the opcode level? When I compile this, this will be created on the right. All right, you can go and do that on evm.codes yourself as well. All this gets created as bytecode to actually construct this contract over here. That's a lot of bytecode, you might say. Yes, it is, but that's just what it is. So how does if we wanted to construct this contract here, how does that look in terms of this blue, green, and white chunks here? What exactly is what? That's what I'm going to show you next. So we're going to take that blue chunk, we're going to turn it on its head. We're going to turn 90 degrees. That's the init code. This is the same blue chunk we had right here. The init code is exactly this purple piece here. This whole piece here, that's that. We can further deconstruct that into its constructor body, and we can further decompose that into the stuff that copies the runtime code, which is the green stuff down here, into memory and returns the caller. So the constructor body is all the stuff up here. It starts here. This sets up the memory layout right here, mstore. It does this thing. That's the memory layout. And then it pushes this onto the stack, which is just the hex representation of 1 ether. And then it checks self-balance. Why self-balance? Because we're doing address of this.balance. That's its own balance, self-balance, and so on. It does all these steps to do. This is just the bytecode for doing these to require is all this stuff here. Okay. Then when it comes down here to the end of doing these steps, again, it takes up a lot of code. But anyway, then at the end, which is not shown, right? We're not explicitly saying, there's no explicit code here that says, please copy the call data or the runtime data into memory, right? The compiler does that for us, and that's what this is. It starts right here in this location, 2B technically. So this pushes 3F is the size of the runtime code, add the metadata. That's 3F is in hex, right? And then it duplicates that, and then it pushes 37. 37, you can recognize down here, 37, that's where the actual runtime code starts. So that's the start of the runtime code. And then it does a code copy. Code copy copies code, this code down here, but it generally copies code into memory. That's what it does, code copy. So you can go look up that opcode as well. And then it just returns. This is the return of the constructor. And then invalid is just kind of a panic code to make sure we never end up there. But this is it. This is a constructor. And again, this you haven't coded up explicitly, but the compiler does it for you. But it's important. Okay, now what is the runtime code? Well, since this contract doesn't have any runtime code, it's very simple, but it still does have some code, as you can see. It actually here sets up the memory environment. You will kind of recognize this. This is the same up here. It always does that. That's just how Solidity and prepares the memory environment. If you go look in the docs, this is what they mean by the memory environment, that the first 2 slots are scratch space for hashing methods. The next slot is the currently allocated memory size, and yada, yada. You can go read more about that, but that is what this is being set up here. So you'll always recognize that. And then what it does is just reverts. You see this, it pushes 0, it duplicates 0, it reverts 0, 0. All right. And then another panic code invalid. We should never end up here. The revert, just make sure they do this revert because they make sure you want to make sure that no blockchain changes have been made to the state, like no state changes have been made. Since there is no code, there should never be any state changes made. That's why they use revert. It ensures that no state changes have occurred. So it's kind of an extra safety thing. And then it'll just be invalid if we ever end up here, which we definitely shouldn't. So anyway, that's what happens. What is all this stuff? Lock 2, push 5, invalid, SLT. This looks weird. SHA-3. What do you mean? We're not hashing anything. What is this? Well, it's just the kind of the bytecode interpretation or representation in the EVM.codes environment of what the metadata hash is. So this is just all, don't read into this. This doesn't mean anything. Just think about this as a chunk of bytes, this whole section here, that just confirms and verifies that this is the correct runtime code and that the compiling happened in a certain way. That's all that is. So we don't need to focus on this. But I just wanted to highlight these 2 pieces. So again, at the end of this constructor, at the end of this purple region, we copy the green stuff into memory and we return it to the caller, and only then can the caller put it on chain. So that's why during the constructor, this contract technically don't exist. So let's take a look at all this now in code. We're going to start with an example I created, and we're going to answer a few questions. One is, can I send money to this contract during construction, even though it doesn't exist? Yes, because remember, the lot is created. The house is not created yet, but the lot is created. So yeah, we can send either. Can I access storage variables during construction, even though my contract code doesn't exist? Yes, because remember, we created the lot. The lot allows us to put this furniture on there, which is these storage variables or whatever you want to call it. So we could put things on the lot, which is the storage. We can also read things from storage during construction. But again, there is no house, so there's no functions. If the house represents the functions and the runtime code, this is not available. There's a detail here. It's not available if it's an external function. So I'll get into that nuance as well. So we have the constructor. It's payables. We can send ETH. And I'm going to show you now as well an additional thing in a second. We'll skip this first. I'm going to show you that we can send Ether, and I'm going to show you this additional thing of reading storage. Okay, so we can do that, but again, there's no functions here on this code and stuff like that yet, and I'll detail what I mean by that. Cool. So now we're going to send one ether to this address here, placeholder, and I'm going to deploy it. You see this succeeded here. So indeed, we deployed it. We also showed that we could read from storage, which is this X here is equal to 1. So we can do that. We can do that. Now what I want to show you, I told you there is no code, we cannot run any functions. However, there's a detail to that. There's a detail to that. During construction, I have access down here. I have access to my own, you can see here, all this is compiled. During construction, of course, I know about my own, I know about my own internal functions. Okay, so during construction, just because there's no code on chain, I can still see my own internal functions and my own private functions, things like that. So anything internal to me, private, internal, even public, because public allows access internally. All these things I can see, and I can actually call that during construction. So I'm going to show you what I mean. This is an internal function. So I can actually call this during construction because it's internal to myself. And it just means that on the back end, in the actual bytecodes, I'm not making a call opcode to call this internal function. Okay, so the compiler just puts this function basically here. Okay, that's why I can call it, because it's internal. Okay, so what I mean by that is what we're going to do is now uncomment that. So I'm calling an internal function. That is fine. Even though the code doesn't exist on chain, I don't need the code to exist on chain to call internal functions. All right, and I'll show you this here. There you go. It got deployed. Everything is fine. But with this require statement, it actually called the internal. Okay, so that's another thing to know, that when you call the constructor, you can call your own internal function because the compiler actually essentially just replaces this with the bytecode behind this. It's not like it does a call to that function. We'll see an example in a second where we call an external function during construction. Now, another example is, let's say we have some existing contract on chain. Okay, again, this could be another contract like this one, like Aave, just some existing contract, some other contract than the one we're trying to construct right now. That's what this is. This existing contract has a function that says, check if I have code, I being this incoming contract, which is during construction, which is in the process of being constructed. All it does is check if I have code, check if this contract has code. It does this by using some assembly. The way you actually check if an address has code or not is you use assembly and you try to get the size of this external code, meaning this external account, external to yourself. What is the size of that code it has? You use assembly to do that. That's not important. The point is just this is how to get the size, or this is a way to get the size. And I just console log the size of that code. All right. So now what we're going to do now is construct this contract up here. So first we deploy that, then we go up here, we construct this, and we're going to call this during construction because we're going to do some stuff during construction. We have our constructor, and we're going to, let's just say, we're going to input this existing contract. Again, this has already been deployed, this existing contract, but we're going to input it here. And then we're going to call that existing contract's check if I have code function, and we're going to input ourselves. So it's kind of like we're doing a self-check here. We're calling some other contract, and we're asking that other contract to check if we have any code during our construction. And it's going to say either yes or no. Well, it's not going to say yes or no. It's going to give us the size, but we're going to see if it's 0 or not. Okay? Does that make sense? So we're asking someone else who's already been deployed, do I have any code? And we're asking it during the constructor. So during the construction body. In other words, let's see it visually. We are going out. Let's show it here. Yeah, right here. We are going out to, during the constructor body, we look like this. Or in other words, I kind of also have it over here. The dashed line means we eventually, when we deploy on chain, will take up this much space. But right now we don't, because we only have this temporary address that I told you about, the lot. The house is not there yet, but the lot. So anyway, so during the constructor body, we are now asking, let's say we ask Aave, okay, hey Aave, what is the size of my code during my construction? Again, they don't have a function to do that, but let's just say they did. Then they will say, hey, I just looked at you, and it doesn't look like you have any code because this dash stuff is not there yet. So you don't have any code. The size of the code is 0. So we know why now, because we only have this temporary address thing here. Okay, we don't have the full code yet because we haven't returned that runtime code to the validator to put it on chain yet. We're not there yet. We are only doing the constructor body. Okay, this is where we are right now. Why? Because we're in here. The constructor body is in here. Okay, so we haven't exited that yet. So anyway, so we're going to ask that question. So we know the answer now. We know the answer is going to be 0, but let's confirm. Let's do this first. We are going to deploy the existing contract. Boom, that's deployed now. Let's say that's Aave or whatever, this kind of contract. All right, this exists now on chain, fine. Now we're going to deploy this stuff up here. All right, so I'm going to go to that contract here. I'm going to grab the address of this contract that already exists, some existing contract, and I put that in as the constructor argument here. And we're going to ask this now, what is our size? Great, let's deploy it. What do we think it is? Well, we know it's 0. You see this? So you see how when we call that external contract, it says the size of the code at address contract, which is us, because that's what's coming in here, and we sent ourselves in there. is 0. And we also, just to confirm, says my code size is 0. So during construction, my code size is 0. Now, we can call this, again, this existing contract, we can call this function once more at this point, because now the during construction contract has been deployed. Why? Because the constructor is done. We have even the address of our contract down here. Everything has been deployed. So now there should be code. So let's actually check. We can now ask the existing contract once more. We're going to grab the address of what was just deployed. And we're going to check the size of this, which is the during construction contract. Now there should be code. So I click, look at that. Now the size of the code at this contract address is 486. So now this during construction does have code there, but it's after the construction, because it's after this body finished running. It's after we copied the runtime code back to the caller, and it's after they put it on chain. So now we're fully on chain. I'm trying to find the visual. Now we're fully on chain here, and we have code. That's what happened when we did this call a second time when we were done with the construction. Cool. Let's take another example. We're really going to dive into now what exactly kind of functions can we call during construction, all right? So first question, can I call my own internal public functions during construction? Well, we know the answer is yes, but let's just confirm again here. We have a public function, which again, public just means it can be accessed externally, but also internally. So the answer is yes, we should be able to do this because it's internal to ourselves. So let's answer that question first. So again, we're going to have some existing contract. This doesn't really matter for this construction. So what we can do, let me just get the, yeah, there you go. Good. So we're going to compile that, and we're going to, again, this will be a broader example. So it will be payable. We don't need the payable right now, but let's just keep it. It's fine. We're going to delete all that, and we're then say during construction. We're going to deploy this existing contract, and we're just going to pretend like this existing contract basically exists on chain, all right? And then we're going to call our during construction. So this exists. We're going to take the address put up here. Again, the address here we're not really using for this simple example, but it's just easier to do it this way. And we're also going to make it payable to send one ETH. That also doesn't matter for this check. All we're checking now is, can I call my own public function, aka like an internal function? Deploy? Yes, I can. So we knew that already. And that's because it's not considered like an external call, all right? But now let's do this. Can other contracts call my functions? So again, during construction, I ask another contract to call any function in my own runtime code. No, because they don't know about my runtime code yet, right? They don't know about it because it hasn't been deployed. But anyway, I'm going to call this existing contract. It's going to have something called some function. Doesn't really matter what it is. That's why it's called that. I'm going to put my own address, myself here as an argument to this, and it's going to call, in turn, my some function. Right? So what happened? I ask another contract that already exists on chain to call back into me and call my function that's called some function. That's this one. So I'm basically saying, hey, it's like I'm sitting on my lot. I don't have a house, but for some reason I have a phone. Maybe I have a cell phone. I make a call to another house on the street and I say, hey, I just moved to the neighborhood. Can you please call the phone in my bedroom or something, whatever. And they do that, and it's like, well, there is no rooms, there's no house, so I can't do that. Okay, that's what's happening. There is no house. All right? So they can't do that. So let's see that happening. Let's see that in action right here. We are going to just start over here. We're going to deploy the existing contract. There you go. And now we're going to do this new one. Now we're going to try to deploy this. So again, we're asking another house in the neighborhood, can you please call some room in my house? Whatever. Do something basically rely on my house being there. And it's not, so there's going to be an issue. Anyway, we're going to deploy this. It's going to be payable. It's not important it's payable for this example, but it will be soon. Anyway, let's deploy this. Boom. There's going to be an error. You see the error here? And the error is basically that we don't exist. Our house doesn't exist. So we don't have runtime code on chain, so they can't call it. I hope you're getting it now. Sorry if I'm going in super, super high detail, but that's a little bit my style here. All right, now we're gonna comment that out because we know that doesn't work. We're gonna do a new experiment. We're gonna say, can I call my own external function? Okay, so can I call my own external function? This is not internal now. I created some external function here. It's external. That's important. So what is the difference between internal and external? The internal is like we have access to it because it's internal to us. So the compiler can know exactly how it looks and like not make an external call to it. When we have an external function and we want to access an external function from within our own code, we need to do this dot something, like this dot that function. So it's important that we need to do this dot that function. We can't just say some external function like this, all right? Because it's not internal. So we need to kind of do this. The point is, by doing this, by having an external function that we're calling from our own contract, it's as if we temporarily become another house in the block and want to call back into our own house, okay? And we can't do that because we know our own house don't exist yet, so we can't do that. So it's as if we like left our house and then we call back into our house. That's what this external does, okay? It's like we leave our house and then we say, oh, by this I mean my own house, by the way, and I want to call this room, living room, bedroom, whatever, in my own house, okay? So imagine it like that. That's kind of the loop that happens. Whereas internal is like I know, internal you can think about maybe like, well, I know I don't have a house yet, but I know exactly how, I personally know exactly how it'll look. So I can kind of, I don't know if that's a good way to think about it, but it's like I can kind of do things. The compiler knows exactly how the house will look, so it can do things, okay? But other people on the street don't know how my house will look, so they can't do things. So I can do that internally. Maybe that's confusing, maybe that's helpful, I don't know. But for the external, it's like I left my own house, and again, my house doesn't even exist. So it's like I pretend for a second I don't know how my house will look too. That's what this means. The external is like I pretend to be an external person and then I call into it, so it doesn't exist. All right. So I don't know if that was the best way to explain it, but that's the reason I can't call my own function if it's external, because I temporarily become another external party or something. Now make the existing contract send ether to us. So what does this check now? Now the payable becomes important. What is this? The question is this: can an existing contract send ether to us during the construction of ourselves? Can they send ether to us? The answer is yes, because again, we have an address that is there to accept ether. So it's like they're sending us mail. We have an address, we have a lot that we purchased. They can send us mail, or in other words, money. They can do that, even though we don't have a house. You don't have to have a house to get mail, so to speak. You just have to have a lot, technically. So that's what this is. So we're gonna send this external contract 1 ether from ourselves during the construction project. We're gonna send this external contract 1 ether. We can also send it ether, and it's gonna send it to us back, and we're gonna confirm that can happen. Okay, so the external contract is this. It's going to receive ether from us, and it's going to send back to us 1 ether. Okay, so can we exchange value during construction? The answer is yes, and we'll see this right now. So let's again do this existing contract. So now the existing contract exists on chain. We're going to copy it. We're going to put it here. We're going to send 1 ether. So now we, as the users, we send 1 ether to our own contract that we're going to start creating. We're going to send it to the constructor. It receives it. We're now going to forward that 1 ether to another house in the street, so to speak, to another contract. That house in the street or that other contract is going to take that 1 ether and actually call us right back. That's what this line does. It calls it right back and sends that money right back to us. Can we exchange value during construction? Let's see. So we're going to deploy that. Yes, we can. Look at that. We're going to have in a second here, this is going to toggle to 1 ETH, but it's a little bit, there you go. So it's going to be 1 ETH. So we sent that 1 ETH, that put our balance at 0. It sent us back 1 ETH, that put it at 1. There was a slight delay, that's fine. So we got our ether back. So yes, we can do that. But can this other contract, when they send back an ether, can the fallback be triggered? Okay, so fallback typically gets triggered when there's no other function that matches a function signature. So you want to call a function on contract, no function matches what you want to call, the fallbacks get executed. But also it gets executed if you just send ether to this contract. If you just send ether, the fallback will be triggered. Did fallback get triggered? No, of course not, because we have a revert right here. So we know that when this other external contract called us and sent us ether, normally if we were a deployed contract, like the runtime code was deployed, the fallback would get called. It didn't get called. We know it didn't get called because we have a revert right here. We also have a console log, and that didn't show up here. Fallback. The sending funds did. That's this one, but not fallback. So this definitely didn't get called. So we can't rely on our fallback function being available during construction either, which shouldn't be surprising because it's just the fallback is just another function, right, in the runtime code. And again, we don't have the runtime code on chain. This shouldn't be surprising. But let's see now, does the fallback code actually work? Okay, so how about we do this now? So what we're going to do is we're going to test that the fallback indeed exists after deployment, which of course also shouldn't be surprising. But anyway, we're going to deploy this existing contract. We're going to deploy this contract here. We're going to take the address. We're going to send it in Ether. So this is the same example we did before. We're going to deploy. Everything is fine. But note that, again, the fallback wasn't called. I used the revert before to really make it clear to you that it definitely wasn't called, or else this transaction would have reverted. But now we can also see there is no console log of fallback. But I can now go to the existing contract, and I can call this deployed contract. Again, now it has been deployed. And I can send it 1 Ether. So what I'm doing now is I'm just calling this down here, the existing contract. I'm calling this function here with the during construction contract that now has been deployed. So it's more like deployed contract now. And I'm going to send it just 1 Ether. And I want to show you that the fallback does get called. That's just like calling any fallback. So of course that should work. So we're going to call this function now. And there you go. Fallback gets triggered. You see that in the log. Fallback gets triggered right here. And that's this right here. All right. So that works just as normal. But it didn't work during construction because the runtime code was not available. Okay? Now, so I hope you understand now. I know this was a lot and this was detailed, but I hope you understand now why this doesn't work. All right? So let's go back to this example and end this with why. So this target is using this contract function to make sure that whoever calls them is not a contract. We know how to circumvent this now because we know now that during construction of a contract, the runtime code has not been deployed on chain, so the size is 0. We just did that check in code. In other words, we can create a hack contract that during construction calls this function is contract. And this will return false. This contract thinks we are not a contract. And we kind of is and we kind of aren't. Because we don't have any runtime code. And that's how you can actually call this protected function, even though you're not meant to do that. All right? So we know now why, because we're just in the middle of the constructor body here in all these calls, but we don't have any runtime code yet. So we're kind of stealth mode. We don't have any runtime. We don't have a house yet. Example 2. In this case, the hacker, the bank robber here, tried to rob the bank during the construction phase of the robbery. During the construction phase, there is no house, so there is no fallback function to be called. So in other words, when they try to do a deposit, that's fine. We can send value between accounts, between contracts during construction. We just confirm that. We can also call external function withdraw as well. That's fine. But here the bank robber relies on when they call withdraw, the withdraw is going to get called up here. This withdraw is going to call back into us. It's going to send us value. It's not going to call, it's just going to send us value. As we know, normally when we're deployed, it's going to trigger the fallback because they send us some value. The problem is we don't have runtime code yet because, again, we are still in the constructor phase, right? The reentrancy happened during this constructor phase. So they call us, they send us value. That will succeed. They will be able to send us value, but the fallback will not be triggered. So in other words, this hack will not happen because this second withdrawal will not be called. So the bank robber will fail. Okay. So the way to fix that technically, if you want to rob the bank, is you can either create a wrapper around this so that, there are 2 ways to do it. You can do it in 2 transactions. You just deploy the bank robber and you just change this function to not be during the constructor, but just be another function called function hack or something. That's fine. That'll work. The other way to do it is if you really want to do it during the constructor in 1 transaction, you can just deploy a new bank robber instance. And again, this would still have to be the wrapper, but you just deploy a new, because during the construction, you can create a new contract. Okay, so what I mean is during construction, you can do something like this. New, like some contract C is new contract. You can do this if C is some contract. Okay, capital C is some contract, any contract. You can do this during construction. And this will create a new, once this line has run, this contract C, lowercase c, will be a valid contract instance of this capital C, and that contract will be fully deployed on chain. So that you can do. That's fine. But so the point is that maybe this gets too complicated, but you can deploy a new contract during construction, and then you can just interact with that C.hack or something. You can call whatever function you want on that. So that's a way to kind of do that. It's like a nested deployment. It's like during my constructor, I can fully construct and deploy another contract and put that on chain. That's fine. And then it returns to me, and I could keep executing my constructor body. But that contract now fully exists on chain and has code in it, okay? And has a fallback function. So we can do that. So that's how you can do that in one transaction. But anyway, the point is now you understand why the fallback fails, why this bank robbery fails, and also why this hack succeeds over here. So I hope you really understand now the exact anatomy of a contract creation. We had the contractor body, we had the final part of a construction that put the runtime code on chain, but doing the constructor body, the runtime was not on chain, so our own code size was 0, and that can lead to some interesting scenarios where we can either hack something or they can hack us. So I really hope you fully understand this now. This was a longer video than normal, but thanks for watching. I hope the visual also helped you understand it. I hope the lot and house and so on neighborhood analogies were helpful. I hope you understand the flow of a transaction a little bit better now to become a better programmer, a better Web3 programmer, a better Solidity engineer. Let me know if you have any questions, and also remember to check out the Rareskills Bootcamp. This is where we go into super much detail about this as well. So thank you for watching, and see you next time.